Welcome to Young Tuition. Let's talk about the partial differential equation for the matter wave in quantum mechanics today. Last time, we have discussed the wave equation for mechanical wave and electromagnetic waves, which is in the form of the second order partial differential equations. Okay. What would be the wave equation looks like for the matter wave? Let's talk about that today. In 1925, de Broglie proposed that the matters, including electron, can also be described by a certain type of wave known as the matter wave. So the de Broglie equation for the wave, the de Broglie wavelength, bear in mind that de Broglie only proposed the formula for the wavelength. So the wavelength is determined by this ratio, Planck constant divided by momentum. And based on these ideas, people argued that we should introduce a wave function to describe this wave. So in general, we can write the wave function as psi. In this case, if we just consider one-dimensional wave, we can simply use x and t, two variables. We can start with using the sine wave to describe this matter wave. Do you remember? That is the formula we derived last time. We use 2 pi divided by lambda x multiply x minus omega t. But gradually, people realize that we have discussed the matter wave in the complex domain. So that is why the wave function psi you are going to use in quantum mechanics is complex variable. That is why the wave function we used is actually a different form that can be used E or exp E. I put the factor here, the I multiply 2 pi lambda x minus omega t. Okay, so I is the unit for imaginary number. And actually, there's a simple formula to transfer the sine or cosine into these exponential forms called the Euler relation. Alternatively, we can write this exponential as slightly different notation, exp, and that would be I 2 pi lambda x minus omega t. So this is a wave function. It's called the wave function. So this is a wave function to describe the matter wave. The matter wave. So this is a wave function. So wave function. For matter wave. De Broglie's matter wave. Interestingly enough, de Broglie only provided the formula for the wavelength, and he didn't tell us what would be the frequency or speed. Okay. So let's talk about these two issues after we derive the formula. Similarly, in order to find the differential equation, then we can simply using the to find the first derivative. Okay. So what we can do the first derivative with respect to the time first. Yes. So in this way, we can immediately obtain that would be, because the negative sign here, we should put negative I omega, and the exponential remain the same. That would be the I 2 pi, and oh, I forgot to write the amplitude here, A. So that is lambda divided by lambda multiply x, take away of omega t. Okay, so first derivative. And again, if you realize this is just the psi, this is just a wave function itself. So we can simplify this expression as I omega and multiply psi. Okay. Instead of go further, we actually can build the what we call the Schrdinger equation now. So can you see, if we just pay attention to this omega, in addition to de Broglie's wavelength formula, Planck also provides, so we have the Planck. Actually, Planck was first person to use this formula to describe the photon energy. So Planck's formula for energy formula is energy formula for the photon. Energy formula can be written as E for the photon equal to h multiply frequency. Alternatively, we can rewrite this as h bar multiply omega, where h bar equal to h divided by 2 pi, and omega, the angular frequency, is equal to 2 pi multiply the frequency. So if you apply the Planck's energy formula, then we can actually obtain the partial differential equation already for the matter wave. Can we rewrite this omega as energy divided by h bar? We got negative I energy divided by h bar here. So this is the first the partial differential equation. And if you rewrite that, if you multiply I, negative I, h and negative I, you can multiply negative I and h bar on both sides. We got this negative I, h bar partial derivative psi with respect to the time, the first partial derivative, were equal to energy multiply the psi, the wave function. Okay. Now, if we just assume that energy, in this case, can also be replaced by the total energy of the electron or any particle, kinetic energy plus potential energy. And also bear in mind, these in analytical mechanics, the total energy is also denoted as a Hamiltonian. So this whole thing is determined by the Hamiltonian. So this is a Hamiltonian. Hamiltonian. H, so H is an operator equal to the total energy. So that's EK plus EP. Then we can obtain the famous equation in quantum mechanics. I h bar, first derivative, dt, were equal to Hamiltonian multiply the wave function psi. So this is a Schrdinger equation. This equation is called the Schrdinger equation. You see, just one differential, by just doing one partial first derivative, we can obtain the famous Schrdinger equation. It's called the Schrdinger equation. In quantum mechanics. Of course, you will see that if you go to detail, you will see that there's an assumption that we can replace this total energy for particle originally in the form of the Planck energy formula. In other words, there is assumption that the total energy of particle can either be described by the Hamiltonian, or the sum of the kinetic energy and the potential energy, as we did in Newtonian mechanics. On the other hand, we also have to assume that the total energy can also, in general, be described by the as a product as a Planck constant and the frequency. So this is a very fundamental issues in quantum mechanics. When we're dealing with the matter wave by using Schrdinger equation, and we actually just pay attention to the wavelengths, right? But by this partial differential equation, it is clear that one have to consider the frequency associated with the total energy of a particle, say the electron in the hydrogen atom, okay? And if we can work out the frequency of the particle, then we can determine the matter wave speed. Okay? Otherwise, the speed of matter wave remains undetermined. I'm going to stop here and have a nice day and goodbye.